Our reason for spending so much time working on linear algebra is in order to be able to solve linear systems, in order to be able to do nonlinear systems. But let's start at the beginning, doing linear systems in continuous and discrete time. Now, for linear systems in 2D, we have two variables, let's say x and y, and we need to see how they evolve over time. So in discrete time, what would this look like? Well, you have xn plus 1 is going to be some linear function of xn and yn. So let's say it's axn plus byn for a and b constants. Likewise, yn plus 1 is a linear combination of xn and yn. It's cxn plus dyn for c and d constants. Okay, so this right-hand side is really just a linear function of the inputs. What's that look like in continuous time? In continuous time, what do we have? We have dx dt is a linear combination of x and y, so ax plus by. And dy dt, similarly, is cx plus dy. Now, we can work with those representations, or we can use the language of matrices and vectors. And of course, that's going to be the way to go. If we pack these four constants, a, b, c, and d, into a matrix, call it capital A. If we pack our variables x and y into a vector, let's call it x. Sorry for the confusion there, but I've got a little underline. I hope that helps. Then in discrete time, we have the linear system x at time n plus 1 equals a times x at time n. Now, I much prefer to write this out using the language of operators. If we use the shift operator e on these vectors, x as a function of n, then we get simply ex equals ax, a familiar equation. What does this look like in continuous time? In continuous time, writing this out in terms of how a vector of variables evolves, we have dx dt equals a times x, or if you like in operator language, dx equals a times x. All right, so in discrete time, we have our vector of variables x in R2. Here's the lemma. The solution to the linear system ex equals ax, having an initial condition x naught, that is x at time 0, is the following. X as a function of discrete time n is a to the n times x naught. Where by a to the n, I mean the nth power of this matrix, a times a times a times a times a. It's a square matrix, so you can do that. Now, is this deep? No. What's the proof? Just follow the dynamics. What is x at time 1? According to the equation, it's a times x at time 0. What is x at time 2? It's a times x at time 1. That's a squared times x naught. Just induct. Just keep going. Now, here's the cool thing. This matches perfectly with what we did in 1D. And this works in higher dimensions as well. There's no constraint based on dimension. We just solved all linear systems in discrete time. Boom. All right, then, I'm feeling pretty good about that. So let's move on to continuous time, see if we can do the same thing. I have our continuous time variable in R2. Here's the lemma. The solution to the linear system dx equals ax with initial condition x naught is, let's see, how's this going to work? I need x as a function of continuous time. I need something that matches up with 1D. I don't know. Let's try e to the at times x naught, because a is like a constant, right? It's like a matrix of constants. Can I exponentiate a? Well, yes, this is correct. This does work. And just like our solution in discrete time, this works in all dimensions. There's nothing particular to R2 about this. But what does this actually mean? What this means is that it's time to recall your basic calculus, because you know how to exponentiate things, right? Here's the definition of the matrix exponential. E to the at is the sum, as n goes from 0 to infinity, of what? I take the thing in the exponent, a times t, raise it to the nth power, divide by n factorial. Just sum all that stuff up. how does that really work? Well, let's think. A times t is a square matrix. When I take it to the 0th power, what do I get? Well, anything to the 0 is 1. Oh, but this is a matrix, a square matrix, so this is really the identity matrix, I. Then I add to it what I get at n equals 1. That is a times t divided by 1 factorial, just a times t. Then I have 1 over 2 factorial times a squared t squared. And that makes sense because a is a square matrix. I can multiply a by itself. Likewise, 1 over 3 factorial, a cubed, t cubed, etc., etc. This keeps going. Now, remembering what we did in calculus class, does this converge? Yes, absolutely. Okay, so what are we going to do with this? Well, let's do the proof of this lemma that the solution to dx equals ax is e to the at times some constant. Let's just work with e to the at. So what I'm going to do is just plug it into the equation, see that it solves it. What is the derivative of e to the at? Well, this is really the derivative with respect to t. So I'm going to differentiate this sum. N goes from 0 to infinity, at to the n divided by n factorial. Now, I'm going to swap the derivative with the sum. And I'm going to take the sum, n goes from 0 to infinity, of the derivative with respect to t of at to the n divided by n factorial. Can I switch like that? Absolutely. When you have absolute convergence, you can differentiate under the summation sign. Okay, now, how do I take that derivative? That looks scary. No. I'm taking the derivative of t to the n with some constants in front of it. So all I have to do is pull out those constants, be a little bit careful. I get the sum. N goes from 0 to infinity of what? N times a times quantity at to the n minus 1, all divided by n factorial. There's a little chain rule going on there. Now, I see that I have an n in the numerator and an n in the denominator from that n factorial. So what am I going to do? I'm going to cancel them, and then I'm going to get the sum. N goes from 1 to infinity. I have to be a little careful with the indexing here because of that cancellation. The sum n goes from 1 to infinity of a times quantity at to the n minus 1 divided by n minus 1 factorial. And now I see what? I see something like an exponential in there. If I re-index, if I say that m is equal to n minus 1, then this really becomes a sum as m goes from 0 to infinity of a times quantity at to the m divided by m factorial. Because a is like a constant, I can pull it out of the summation, and I get a times, by definition, e to the at. And that's it. That's our proof. Now that's a swell proof, and I'm pretty happy right now. We've solved ex equals ax. We have to compute a to the n. We've solved dx equals ax. We have to compute e to the at. But how? Let's start with the simplest possible example where a is a diagonal matrix. Let's call those diagonal entries, how about lambda 1 and lambda 2? Then, what does it mean to take powers of this? Well, that's simple. The nth power of a diagonal matrix is you take the diagonal entries, raise them to the nth power. Easy. How are we going to compute the exponential? Well, to compute that, we just have to take powers of a, and then multiply by t to the n, divide by n factorial. When we do that, we're going to get the diagonal matrix e to the lambda 1t, 0, 0, e to the lambda 2t. This corresponds to a decoupled system, so of course the solutions that we get are really just the solutions to the one-dimensional problem. That makes sense.